Let's start the next session about cryptanalysis of stream ciphers 2. This session has two talks. The first talk is about significantly improved cryptanalysis of SALSA 20 with two-round criteria, given by Sabyasachi, Subamoy Maitra, Santan Sakar, Nitin Kumar Shamal. The speaker is Nitin Kumar Shamal. Please give your talk.
Thank you for the introduction. Good morning, everyone. Myself, Nitin Kumar Sharma. I'll be presenting my work entitled as Significantly Improved Cryptanalysis of SALSA 20 with two-round criteria. This is a collaborated work with my supervisor, Professor Sabyasachi Day from BITS Pilani, Hyderabad campus, India. Professor Shubhamay Mitra from ISI Kolkata, India. Professor Shantanu Sarkar from IIT Madras, Chennai, India. The only paper with all the Indians. So I'll give the overview about my work. So first I'll explain the design of SALSA 20, our novel techniques, the two-round criteria that we have mentioned in the title, influence of PNB IV bits, probabilistic independent IV bits. Then on these two ideas, I'll explain the cryptanalysis of 256-bit and 128-bit key version of SALSA 20. Then we have analyzed previous works also, so I'll give a idea about that. In the end, I'd conclude and followed by references. So I'll give just idea about SALSA 20, what it is. So it is an ARX-based cipher designed by DJ Bernstein in 2005. So the state looks like it's a 16 word structure. As you can see, the blue elements are keywords, K0 to K7. Constants are C0 to C3. And we have IV bits, initialization vector, V0, V1, T0, T1. These are 4 in control of the analyst. And the round functions look like this. What we will do, we will pick any, we'll start with first column, we'll pick 4 elements, and then we, let us suppose we say that A, B, C, D are picked, and then they are transformed as B dash, C dash, D dash, and A dash as given in 1. So this is how the encryption process works. We pick the columns and then we go to rows. Columns, completing the columns makes a 1 column round. Then rows, completing all the rows makes a row round. So 10 rows, 10 columns, and then 10 rows make SALSA 20. So the name comes from 20 rounds. So it has 10 column rounds and 10 row rounds. After the completion of n number of rounds, whatever we require n, we do the addition, matrix addition with the initial state, and then we get Z. This is required for, this is a key stream block, and this is a reversible process. So we, in the reverse round, we also go from A dash to B dash in the reverse order, and we obtain the elements. So this is a rough idea about design. I'll explain my 2 ideas that we have used here. So we have applied differential linear cryptanalysis in SALSA. What we do in that, in the differential part, we used to find right IV pairs. That has been used from probably Crypto 20. This idea was introduced that we should partition it into 3 parts. First part would be differential part, where we will look for key IV pairs. So the idea is we do introduce a difference in the 0th round, and then we look for number of differences after 1 round. So it was limited only to 1 round. We extended it to 2nd round. So what happens that earlier used to happen, the first statement that after completion of 1 round, we used to look only for 4 differences after 1 round. 4 differences after 1 round. So what we have done, we know that the difference is in the X15, the 2 differences. We try to control the 2 differences, the difference in the bit 70 and 30, so that only 2 differences goes to X12. So the condition becomes 4 differences after 1 round and 2 differences in X12 after 2 rounds. So what we have done, we have increased the round and modified the key IV pair finding criteria. That's the right pair idea. Using this criteria, what we achieve, we improve the differential bias, epsilon D. So earlier attacks used one round criteria. So you can compare the bias values we have modified and improved by a margin of 2 power 4 overall, but we haven't limited up to this point. What we have done, instead of going for individual biases, we have combinedly obtained the bias of second and third value. So instead of going for 2 power 20 point something, we got 2 power minus 16.23. So we have combinedly find the bias for these two values, the XOR value, and using piling up lemma, we achieve it to 2 power minus 33.75. So you can see we have improved by 2 power 8.25. So the bias value, if you look, it has already improved by a big margin. So it has ultimately improved the time complexity. But what we have done, we have moved to next round, second round. So due to this condition, we controlled two things. What we control the difference at two positions. Due to this, the p value in the differential part increased to 1 by 8. Earlier it was 1 by 2, but it increased to 1 by 8. So this thing we lose in the sense of adding the criteria. But as you can see, the bias is is improved highly, so we can manage with the values. Now this is one thing that we have done in our work. The second thing is, as I mentioned, that we are controlling IV positions. So in one round criteria, we used to control one IV position. So we had the condition on n, that the value of n can be maximum 2 power 98. This criteria, please keep in mind, I will use this thing again and again. So what happened, we controlled one another IV bit, which reduced our n value by 32. So we were limited only to keep the value of n by 2 power 64. But we also did work on this thing, and we combined the condition in such a sense that we modified the n formula. In previous work, this p1 value was not involved in this formula. So what we did to improve the value of n to its original value of 98, we select the IV bits, PNB independent IV bits, using this algorithm in such a sense that we select only those IV bits which satisfy this criteria, two round criteria. So in that sense, we kept the limit of n equal to 2 power 98. So this is also the work that we have done. We have included the PNB IV idea in the data complexity value. Now we have modified the n value. In one of the work by Day, he has modified the complexity calculation formula. In what, as we are aware of the PNB idea, probabilistic neutral IV bits, what we do, we divide the key bit into two parts, influential key bits and non-influential key bits. We work on those key bits and we try to increase the size of PNB bits. So we have to work less. We have to for the key recovery, if we have less influential bits, it will be good for a cryptanalyst. So what he has done, he has, instead of just going for the XOR PNB for the XOR value, we have obtained PNB for each OD bit position. So OD1, OD2, ODK, we have obtained PNB for every position, and then the set of PNB increase. This help us in improving the complexity. So the formula is given by here. Here I'll tell you a few things. Earlier, the formula of epsilon was epsilon D into epsilon A. Epsilon D, I mentioned the forward round or forward bias, the differential bias. This was backward bias that was obtained only for XOR value. This epsilon I is the correlation or bias value for each OD bit position that we obtain. In this formulation, small m indicates the non-PNB bits corresponding to the XOR value. Mi corresponds to non-PNB for each OD position. K is the number of OD position, and R minus R is the reverse round. So I'll explain it context of 256-bit salsa, then you'll get a proper idea about that. So what we are doing here, see, we are introducing a difference at 31st position of x7. X7, you have seen the 7th word. 0 indicates 0th round. And then we have modified the epsilon d value for these 4 positions that I've shown in table. Now these 4 merges as a single in 5th round. So the correlation is 1. Now to use the formula 3, we have linearly extended it to 6th round. So here the value of k is 4. So you can see the k here is the number of OD position. So here the positions are 4. So what the criteria is, we'll find the PNBs for the XOR value, and then we find PNB for each bit. So this helps in increasing the PNB count, and ultimately we'll get a good complexity value. So the overall bias for this complete differential is 2 power minus 35.75. Now I'll explain it in context of 256-bit key version of salsa. So what actually happens in design, why there is 256 and 128, the key you are seeing, its total comprises of 256 bits. So if the 4 initial key bits are copied as same, it will turn into 128-bit. If you are randomly choosing all the key bits, then it is 256-bit key version. If you are repeating 4 above in the below part, then it's 128-bit version. So what we have done for 8 round, we have obtained 160 PNBs. The epsilon A value for the XOR part is 0.0039. And then I've explained the PNB IV bits idea. We got 98 such bits, and the value is of P1 is 0.85. That will directly insert in the N value. And for each OD bit, as you can see, there are 4. So there are 4 correlation values: epsilon 1, epsilon 2, epsilon 3, epsilon 4. And the complexity formulation as given in equation number 3, we have obtained. See, you can see here the k is 4, r minus r is 8 minus 6 equal to 2. So the total round is 8 for 8 round attack. We have differential up to 6 round. We are going back 2 rounds. So 8 minus 6, the reverse round we are going. And as I've mentioned earlier, the p value changed to 2 power minus 3. In previous attack, for 1 round criteria, it was only 2 power minus 1. But you can see that the epsilon value in our case is minus 44.38 after doing so much of things. But in previous, it was already 2 power minus 42.01. So we have improved a lot. So this is complexity for 8th round. And we have, due to our criteria and the techniques, we were able to manage the first ever attack on 8.5 round. We have obtained 100 PNBs, and the bias value is 0.0034. We have done the same procedure, finding bias for 4 OD positions. And we have managed to provide the time complexity as 2 power 245.84 after multiplying with the p value. And you can keep an eye on this thing, that we are always keeping the n value below 2 power 97. Similarly, we have done it on 128-bit key version. For 7 round, we were not managed to get a huge margin, so we change our criteria and put it on 2 IDOD pair things. And this work is done in our IndoCrypt work in 2022. We have come up with 2 IDOD pair technique, and the formulation is given here. If you use 2 such pairs, you have to use the time complexity formula as this, and data complexity formula as given by this. So you have to separately find the value of N1 and N2, and then you can easily find the complexity. It's a simple calculation. And similarly, we have done it for 7.5 round, but the criteria is single IDOD pair technique, and we managed to get a good attack on 7.5 round. So the time complexity is 2 power 111.47 with multiplication after multiplication by p equal to 2 power minus 3. So these are the attacks, and you can see the conclusion that for 7 round of 128-bit, we managed to cover 2 power 4 by 2 power 4 we have improved. For 7.5 round is 2 power 13, and if you compare it with for 8 round of 256-bit key version, then it's 2 power 31. If you compare it with the valid attacks, then it's 2 power 54. I'll talk about the valid and invalid thing. And for 8.5 round, we are the first one to give an attack. So here you can see these are star marked. The reason is in the next slide. So as I mentioned that for 1 round criteria, as we are controlling, we are giving input difference at 1 IV bit. So we have only a limit of n to be 2 power 96. But in these two works on 7 round and 8 round, the data complexity is always greater than 2 power 97 after multiplying by p. So 1 round criteria, what it does, like after getting the n value, you have to multiply by p 2 power 1. So the maximum is 2 power 97. But here in these works, it is always greater than 2 power 97. So they didn't focus on this part. And also what happened in this case, that when they were finding the time complexity value, there were some errors in correlation values. So we have corrected that. So the complete detail is given in our work, that how data complexity value should be kept and what are the changes that they should have done to keep it within the limits, and correcting those errors, we have properly mentioned the values. So if we compare with those modified and correct values, we have still improved a lot. So I'll conclude my talk with this things, that what we have done in this work, we have modified the right pair idea and moved it to 2nd round so that we can improve the bias values, and we can use it further so that we can provide a solid right pair technique. And this PNB IV technique was not used in context of SALSA, and the merging with data complexity value was never done. So we have done that also, and we have done a solid work on SALSA 8 round of 256-bit version, and you can see the improvement. And with these ideas, we are the first one to give an attack on 8.5 round. So these are the references that I've used during this work. Thank you, everyone.
Thank you for your nice talk. Are there any questions or comments? Okay, let me ask a quick question. Do you think the 2-round criteria could be extended to 2.5 or even 3 rounds?
Yeah, but then as we have seen that p values increases with every control. So for 2-round criteria, it moved to like 1.8, 1 by 8. So if we do that, we have to manage with other things also. So there will be a multiplication of 1 by 2 if we control every part. So we control 2, it got multiplied by 1 by 4. So we have to think a little bit on that also, that there is a multiplication in that factor.
Okay, thank you.
Thank you very much.
Are there any other questions? Oh, sorry. Okay. So let's move on to the next talk. So let's thank the speaker again.